Hi everyone, my name is Seon Raghavan. I'm a PhD student at MIT, advised by Vinod Vaikuntanathan, and I'm very happy to be talking about our work on cloning games together with Alex Poremba, who's now faculty at BU. And we talk about applications to black holes and cryptography in our paper. I'm mostly going to focus on the cryptography for this talk. So the star of the show today is the no cloning theorem, which informally just says that quantum information can't be copied and pasted. If I give you a quantum state, it's impossible to produce two copies of that same state for a generic state. And moreover, we also have robust variants of these due to Werner, which basically says that it's not even possible to generate something that's close to two copies of the initial state in trace distance. And the reason why this is so exciting as a cryptographer is it provides hope for unclonable cryptography, which is any cryptographic application where we want to safeguard against the duplication of information. And classically, this is completely impossible because you can copy paste anything, but quantumly now it becomes a possibility. But the no cloning theorem just provides hope. It's rarely sufficient, which is a point I want to get across. And the thing we'd really like for cryptography is what I like to think of as useful no cloning theorems. So, a useful variant of a no cloning theorem, which is even stronger than a robust no cloning theorem, is that it's not even possible for both states produced by the adversary to have some property in common with psi. And what exactly this property is depends on the application that we're working with. So let me dive into the example that I'm going to be working with throughout this talk. So this is unclonable encryption, and this was kind of first defined by Broadbent and Lord in 2020. And the setting is as follows. So Alice on the left has some message that she wants to encrypt, a message X that she wants to encrypt under a secret key theta. And so this game, and we have three adversaries, Clarence, P1, and P2. Okay, so let's step through this game step by step. So the first thing that happens is Alice samples a key theta, uh, and then sends this quantum ciphertext state over to Clarence, encrypting X. And now Clarence is allowed to do whatever he wants with this state, and eventually he sends some bipartite state to P1 and P2. Okay, and later, P1 and P2 get access to theta, so theta is revealed. And what we'd like to, and what we'd like, and the adversaries win if P1 and P2 both have guesses for X, and those guesses are correct. Okay, so just as a starting observation, if the ciphertext state were a classical string or otherwise clonable, then this would be completely impossible because Clarence can just clone it. Now he has two copies, and then he sends them over to P1 and P2. And that's that. Then when they get theta, they can later just decrypt, and now they both have X. So what we want for useful no cloning to get secure unclonable encryption is that Clarence should not just be able to. We don't just want to prevent Clarence producing two copies of the ciphertext state. We also need to prevent Clarence from producing any two states that reveal X, given theta. Okay, so with that in mind, let me dive into some slightly more precise definitions. Okay, so the slides I talked about earlier was search security, right? The adversary success metric is actually requires them to completely recover the original plain text message. So formally, the value of this game is the probability over, the randomness of the key theta, and we're also going to assume the message X is uniformly random. It's the probability over these things that both guesses are correct. Okay, and for such security, we would like the value of this game to be negligible. But now I'm going to shift to multi-copy search security. And now this behaves as follows. So now what happens is that you'll notice that we have T plus one players down the bottom instead of just two. And Clarence gets T identical copies of the same pure ciphertext state. And then he can forward whatever he wants to T plus one isolated players. And now it's exactly the same. The value of the game is the probability that all T plus one players can correctly guess X. So the T equals one case is what I was talking about up to now. And once again, for search security, you want the value of this game to be less than or equal to negligible. You could ask for a stronger notion of indistinguishability security. So We don't particularly consider this setting. I'll say a little in a bit about related work and indistinguishability security, but for this talk, search security is the only game in town. Okay, so with that, we're going to focus on multi-copy search security. And just for some context, like what is kind of a naive strategy that we, can't hope to defend against. So I claim that there's always a strategy that achieves probability 2 to the minus n. And the way it goes is that Clarence forwards one copy of, so that Clarence has T copies of the ciphertext state. He's just going to forward one copy to each of the first T players. So now, those T players, once they get theta, are going to be able to decrypt and recover X. However, PT plus one knows absolutely nothing. So they're stuck at having to guess randomly. So they will just guess a random string, and the probability that they succeed is 2 to the minus n. So this is kind of a baseline strategy. Okay, and the ideal goal given that would be a construction which doesn't admit any strategies achieving better than 2 to the minus n. That would really be the dream. Okay. So with that, let me talk a little bit about what previous candidates looked like for unclonable encryption. So one is BB84 states. So here we think of the key and the message as having the same length, so theta is also an n-bit string. And now the ciphertext state is, I'm denoting it by x to the theta, but what it really is I look at theta to decide whether to encode x in the standard basis or in the Hadamard basis, and then I accordingly encode x. So it could either be 0, 1, plus or minus, and that's my ciphertext state. And previous work actually showed that this is a perfectly, sorry, not perfectly, but it is secure when t equals 1. In particular, they actually show exactly that the value of the game like exponentially decays with n. So it's not the 2 to the minus n that we would ideally want, but it's still very good. However, the bigger issue is that once I give you even 2 copies, this is completely broken. The adversaries can win with probability 1. And let me describe that strategy to you. So what Clarence is going to do is he's going to measure one copy in the standard basis. So Clarence has 2 copies. So he's going to measure one copy in the standard basis as if theta were the all zero string. And then he's going to measure the other in the Hadamard basis as if theta is the all one string. And now he's just going to forward these results to all players. This is completely classical information. He can send it out as much as he wants. And now the point is that the players later are going to actually learn theta. And once they do this, they know which bits were encoded in the Hadamard basis and which were encoded in the standard basis. So they can mix and match the 2 results that Clarence gave them to recover X, and now the players just win. Okay, so that's not good at all as far as multi-copy security goes. Let me talk about another candidate, which is subspace coset states. So here things look a little bit different. So the key is a random linear subspace of f2 to the n of dimension n over 2. And then, we're going to pass a message x as 2 cosets, a plus s and a perp plus s prime. This is just some canonical map that I'm assuming exists. And then we define the state a sub x or a sub s comma s prime to be the following. So it's almost a uniform superposition over the subspace A shifted by S, so it's a coset. But then I also have a phase that depends on S prime. So that's what the ciphertext state is going to be. And previous work also studied this game in the single copy setting, and once again they could show like a slightly worse but still exponentially decaying upper bound on the probability on the value of this game. However, once t becomes a large enough polynomial in n, this is again completely broken. And the reason is simple. So Clarence's strategy is going to be to measure many more than n over 2 copies in the standard basis. And this will essentially allow him to learn a plus s, the coset. And then he's going to measure many more than n over 2 copies in the Hadamard basis, and then that'll let him also learn s prime. So with these results, he can recover a, s, and s prime with good probability. And now he actually knows the secret key. He knows the secret key and the message, so there's nothing to do. He can just tell P1 through to PT plus 1 everything. And they actually don't even need to be told A. Clarence could just as easily have told them. Okay, so this is also not multi-copy secure. And the takeaway you should the takeaway from this is that any class of states that's learnable is definitely not going to suffice for multi-copy security. Because if Clarence got enough copies that he could actually learn the state, then it's game over. He can just send the players a classical description of the state. Okay, so with that, let me shift to our model. It's pretty hard to it's pretty hard. It seems pretty hard to find satisfactory multi-copy constructions. So we made the problem slightly easier for ourselves. We shifted to a restricted single oracle query model. So now, instead of giving the players P1 through to PT plus 1 data in the clear in the final phase, instead what we're going to do is we're going to give each of P1 through to PT plus 1 oracle query to the decryption functionality. Um, and yes, of course, this is not ideal, but Oracle models have been used in other works on unclonable encryption, and the hope is, of course, for these constructions and security proofs to be lifted to the plain model later. And I want to say two things about this model. So first, it still enables the trivial 2 to the minus n strategy because that only requires one query to decryption. And secondly, it still enables attacks on learnable classes of states because those don't require any queries at all, actually. So kind of all the attacks I've talked about up to now kind of still hold in the single oracle query setting. Okay, so with that in mind, let me talk about our results. So we give the first candidate unclonable encryption scheme that's plausibly multi-copy search secure for any polynomial number of copies. We don't quite prove that, but our construction is based on binary phase states, which are pseudo-random, as I'll say in a bit, and therefore unlearnable. That was kind of the inspiration for this construction. And we don't prove the scheme's security, but we provide evidence towards it. In particular, we provide a security proof when t is much less than n over log n in the single oracle query model. And in fact, provided the number of copies t is constant, any constant, the success probability bound that we show is actually order of 2 to the minus n. So this is essentially tight, and this is something that was not true of any of the prior works or prior constructions. And previous work did show how to do this when t equals 1 with large ciphertext states with more than n qubits. But our ciphertext states are just n qubits to encode an n-bit message. And moreover, another contribution of our paper is an application of our t equals 1 results at a single copy to black hole physics. So that's Hawking radiation decoding. And I want to note that, the two properties that I mentioned above, the order of 2 to the minus n, the tight exponential bound, and the ciphertext states only comprising n qubits, these are not just intellectual curiosities. They are actually vital for the application of our result to black hole physics. So, we get a construction that achieves both of these, and then that enables this application. Okay, cool. So with that aside, I want to briefly pay lip service to all of the work that's taken place over the years on unclonable encryption. So I have this comparison table. So in the second column, we have security and the security notion. And so I mentioned earlier that for this talk, we focus on search security, but other works also very rightly consider the important question of indistinguishability security because that's the gold standard. Getting proofs here is like a notoriously difficult problem for reasons I won't get into. So yeah, there's a mix of search and end. And then in the third column, we have the number of copies. And then we have assumptions and other caveats. So our work is in the fourth row. I want to call attention to two really amazing works that came out subsequently. So one is by Bhattacharya and Kalf, where they actually managed to prove indistinguishability security with a single copy. There's no computational assumptions. It's completely information theoretic. The catch is that the distinguishing advantage is just 1 over poly. I also want to call attention to an even more recent work by Chuck and et al. That prove a really fabulous result. They get search security for an unbounded polynomial number of copies. So we just get n over log n, but they can do an unbounded polynomial number of copies, assuming IO and one-way functions. But given how difficult these problems are, I think those are perfectly reasonable things to assume for now. Okay, cool. So with that in mind, let me say a little bit about our construction and analysis. So let's take a detour into pseudo-random states. So let me start by telling you what those are. So they're specified by a function gen, which maps lambda bit strings, so those are the seeds, into n qubit states. And the goal is that the following two distributions are computationally indistinguishable for any t that's polynomial in lambda and n. So the ideal notion is so the ideal setting is where you take t identical copies of the same Ha-random pure state. And the pseudo-random case is where we, take a random lambda bit string, put it through our pseudo-random state generator, get some pure state, and then give t identical copies of that. So we want these to be computationally indistinguishable. And these have unclonability properties, right? So Werner showed that Ha-random states are multi-copy unclonable. So then by PRS security, we immediately also get that pseudo-random states are multi-copy unclonable. And this is why they become a natural candidate for unclonable encryption. Okay, so with that, let me tell you about the pseudo-random states construction that we're going to be working with. So this is what's known as binary phase states. And the idea is as follows. So the ingredient we need for the PRS is a PRF, a pseudo-random function. And then our pseudo-random state is as follows. So I take in a PRF key as input, and then the state that I output is a uniform superposition over n bit strings, except I then apply a phase that's the PRF applied to whatever's in the register. So that gives you this expression. And these two earlier works show that this is indeed a pseudo-random state. And there's an alternate way of writing this, which will be useful for us, which is as follows. So I can think about f in terms of its phase oracle, u sub f. So this is a diagonal unitary with -1 to the f z down the diagonal. And then this is just taking the plus state or the Hadamard state, the Hadamard unitary applied to 0 to the n, and then applying u sub f. So you get u sub f, h tensor to the n, and then ket 0. Okay, so this is the construction. And with that in mind, let me kind of state our construction. So if you wanted some modestly secure one-time secret key encryption using a PRG, what would you do? You would, given a key K and a message M, you would output M XOR PRG of K. And our unclonable secret key encryption scheme is extremely similar, except instead of doing XORs, we now apply a Z gate. So to encrypt a message X, first what we do is we expand the key to a pseudo-random state, and then we apply a Z to the X gate. So what this looks like, if you kind of work out the calculation, it's now u sub f, h tensor to the n, ket x, rather than ket 0. Okay, so this is it. And then decryption, the decryptor knows what f is, so they can apply a u sub f to cancel that out. And then they just apply a Hadamard gate, and then they have ket x, so they can just measure in the standard basis. So super simple, that's our construction. And just as a refresher, thanks to Werner, we know that these states are not multi-copy clonable by a computationally bounded adversary. But once again, our goal is to prove a stronger theorem, which I think of as useful no cloning. We want to say that the cloner Clarence cannot construct any t+1 states that reveal x given k. And this is why we go to an oracle model to hopefully make this goal easier. Okay, so with that in mind, let me give a little teaser of how our analysis works. So I've just taken the same security game, but just drawn it at the top of the screen. So this is what the game looks like, right? So step one is kind of a straightforward one. We're just going to pass from the PRF to a truly random function. And this is the only step where we're using the fact that the adversaries are computationally bounded. We use PRF security, and then that's that. Now we're just relying on the single query assumption. Okay, cool. So now f is a truly random function. What now? The second step is to switch to an entanglement-based formulation, where instead of Alice sending Clarence a state, instead they begin the game sharing entangled qubits, And then Alice kind of teleports her state over to Clarence. So you can think about it as a teleportation style thing that's going on. So in more detail, what does that look like? So Alice and Clarence start by sharing NEPR pairs. And now we can also reorder the operations in the game. So Clarence can act arbitrarily on his half of the EPR pair, and then forward some states to P1 and P2. Okay, so this is before Alice even knows what the message is going to be. And then Alice samples f from the function family and then applies h tensor n and then u sub f to her half. Sorry, u sub f and then h tensor n. And then she measures her side of the state in the standard basis. And this is effectively like teleporting the ciphertext state over to Clarence if he didn't already send stuff to P1 and P2. So now P1 and P2 make one query to U sub f and output their guesses. So what we've gained by doing this is that we now have a game where you can think of Alice, P1, and P2 as all making simultaneous measurements depending on f, and the adversaries win if all three measurements give the same result. So some of you might recognize this game here, and this is a monogamy of entanglement game. And a lot of previous works on unclonable cryptography apply this transformation to shift into a monogamy of entanglement game. And the reason for that is that we have existing techniques for analyzing monogamy games due to Thomas Michel et al. However, these face two problems. So one is that you can only ever hope to prove an upper bound of 2 to the minus n over 2 on the winning probability. This is something we show formally in our paper. And we'd like 2 to the minus n. And the second thing is that you cannot prove any meaningful bound in the multi-copy case using this monogamy formulation. And this is also something that we show in our paper. So these limitations are broadly nice for unclonable crypto. For our purposes and our goals, they don't suffice. So our approach is to analyze this game using binary types, which were introduced by Anand et al., and a novel generalization, which is new to our work, called subtypes. Okay, so that's as much as I want to say about, the analysis in terms of the first few steps. I just want to highlight a standalone, linear algebraic tool that we had to introduce to prove our results that's hopefully of interest elsewhere. And you'll just have to take my word that the analysis boils down to bounding the operator norm of something that looks roughly like a tensor product of block matrices. So let me describe the result we prove, and hopefully it's of interest to someone else. So I have these complex scalars, gamma ij, of magnitude at most 1. And then I'm going to take two R by R block matrices, A and B. And these are some matrices, each of which has spectral norm less than or equal to 1. And then I want to consider this object. So this is once again an R by R block matrix. And in each block, what I do is I take the block from A, the block from B, and tensor them. And then I also scale by the corresponding gamma. And the claim is that if you do all of this, the resulting matrix also has spectral norm less than or equal to 1. If the gammas weren't in the picture, or equivalently if the gammas were all 1, this is not too hard to see because this matrix is a submatrix of A tensor B, and then you would be done. But with these, arbitrary gammas in the picture, things get a bit more complicated. But you can look at our paper for details on how we prove that. Okay, so maybe in the interest of time, I'll skip over the summary of our construction. I'll just briefly say that the value what we prove in the single oracle query model is that the value of the game is at most 2 to the order of t log t minus n. So provided t is constant, this is order of 2 to the minus n, and when t is much less than n over log n, it's still negligible. And the other thing I want to highlight is that I think our belief is personally that we expect this to be actually plausibly multi-copy search secure for any polynomial number of copies. It's just that, this is as far as we could push our techniques, but I think it would be nice for future work to try and, actually prove that. Okay, so with that, let me close with some open questions. So firstly, can you prove a stronger security notion for our construction? like I said on the previous slide. And secondly, can you get multi-copy security from milder assumptions than IO? Um, so uh, this next bullet is actually a typo, sorry. It can't exist unconditionally due to, for example, using tomography. But it could definitely exist with much milder assumptions, like, say, one-way functions or something even milder. Um, okay, cool. And finally, can we get indistinguishable security in the plane model with classical decryption keys and distinguishing advantage negligible in lambda? And this is open even for the single copy case. All of the works I described several slides ago, have some caveat on at least one of these fronts. I think this is a super crucial open problem. So that's all I have to say, and thanks very much for your time and for your attention.